Hi, in this video, as you can see, we're going to talk about aggregate models and a very surprising result to me from statistics called Central Limit Theorem. Okay, so let's. The setup is going to be the same as it has been in the last few videos. We're going to assume that we have a collection of independent and identically distributed random variables with a common distribution of cap x. And so I'm going to think about, initially anyway, I'm going to think about cap x sub I as being the random variable representing the amount of an ith loss. So I'm thinking of I have a collection of losses, and I'm going to add up all those individual losses to get the total loss. So I'm thinking of cap x sub I as being, again, the random variable representing the amount of the ith loss. This is referred to on the STEM exam. It's referred to as a severity random variable. And then I'm going to define cap s to be my aggregate or total loss random variable. So I would add up all those individual losses like we just discussed. And I would add them all up, and I could use sigma notation as a shorthand notation. Now, I'm going to put another sum below this, and notice the difference between these two sums is very subtle. I just used, in the first sum, I used a lowercase n, just an n, and in the second sum, I used a capital N. And so in the first sum, I'm thinking of n as being an unknown but fixed value. It's just, I don't know what it is, but it's some fixed value. In other words, it's not random at all. Whereas in the second one, you're used to this, I'm sure by now, that you should be. Then I use capital letters. I'm using a capital letter to represent a random variable. So cap n is a random variable. And so there's a subtle difference between these two. The first sum is a sum of a fixed number of terms. The second sum is a sum of a random number of terms. The cap n in the second, at the very end here in the second summation, the cap n is often referred to on the STEM exam, or it is referred to on the STEM exam as the frequency random variable. So you have a severity random variable and a frequency random variable. This particular sum, if you're on this exam, exam P, if you see anything with this particular sum, the question is probably going to ask you to calculate what the variance is of the sum, and the approach to take is to use the law of total variance, this beautiful formula that's in red there. Use the law of total variance to calculate a variance of a random variable, an aggregate sum where the frequency is not known, but the frequency is a random variable itself. Okay, there I did an example on this, so see the video on summing independent random variables, and at the end of that video there's an example on exactly this situation. But for the rest of this video and on exam P, primarily the types of problems that you're going to see are the problems where you have a fixed but unknown number of terms, or you might have a known number of terms. Anyway, so let's look at a summation like this. This is a general summation now. So generally, the cap x's here could represent some other random variables. They could be random variables that represent some other property, not necessarily losses, but just could be anything. And the point here also is that I have an independent and identically collection of random variables. I've got a common distribution cap x, but the distribution cap x could be any distribution at all. It could be even a discrete distribution. It doesn't have to be a continuous distribution. So any distribution at all. The central limit theorem says that if you have large values of n, so if you're adding up a bunch of these terms, then the sum is approximately normally distributed. That's pretty interesting. That's a surprising fact to me, that you might have this random variable cap x, the common distribution be some other type may not even be a continuous distribution. It might be a discrete distribution. It could be just any type distribution. It doesn't even have to be a parametric distribution. It might just be given to you in table form or something like that. But when you add up an independent number, if you add up enough of these, in the sum there, if you add up enough of the independent random variables, you'll end up with approximately a normal distribution. And the other surprising fact of this is it doesn't take really that many terms to add up. Normally, if the standard is if you take more than 30 terms, you add up 30 or more of these, or more than 30 terms, then you can generally assume that you have a normal distribution there. So that's an important fact. It's called the Central Limit Theorem. I believe the word central means that it's just it's central to the study of statistics. That this fact is just a very important fact that's central to the study of statistics. Okay, so now what I'm going to need in the next few slides is I'm going to use the fact that I have an identically distributed collection of random variables. And so I got CapX as the common distribution, and I'm going to look at, because I know that I'm going to be using a normal distribution, I'm going to need to know or just write out what the notation is for the expected value of CapX and the variance of CapX. So I'm using this notation. Notice I'm using a subscript of CapX on the mu and the sigma squared here. And that's kind of illustrating that later on in the video, I'm going to change the subscript to different letters. Okay, so that's where we're at. Now, again, I know that CapS now, let's assume that we have more than 30 observations that we're, or 30 variables that we're adding together, and I know then that CapS is approximately equal to a normal distribution. So the question is, well, what are the parameters that I use? Well, the first parameter for that normal distribution is the expected value of the random variable, and the expected value of a sum is the sum of the expected values. I've got identically distributed random variables. CapX sub i's are all identically distributed, so all of those expected values are just the expected value of CapX. I can drop the subscripts, and the expected value of CapX I'm using as I'm going to use the notation that's a mu sub CapX. And now how many terms I have in the sum is the n value here, and so the expected value of CapS is n times the mu for CapX, mu sub CapX. And likewise, let's look at the variance. The variance of the sum, well, because of independence now, the variance of the sum is the sum of the variances. And by identically distributed, I can drop the subscripts. Each one of those variances is equal to the variance of CapX. And I have n of those also, and I'm using sigma squared sub CapX as the variance. And so I'm going to have, for the variance of CapS, I'll have n times the variance of CapX, or n times sigma squared sub CapX. Another random variable that you're going to see on this, in fact, in some cases, they actually define the central limit in terms of this other random variable, and it is the average of all the CapX sub i's. And so if you take to get the average of all the CapX sub i's, I would add them all up and then divide by the number that I'm adding together. So that's n. So, and then I can think of that as just the CapS random variable divided by n. Instead of using the letter cap A, I'm going to use what's commonly used here, is that a bar over CapX. So CapX sub bar would be the average of the CapX sub i's. Now, the fact is, if you look at the last equation there, the last expression, I got a cap S divided by cap N. So I can think of cap X bar as being a constant times cap S, the constant being 1 over N. And the fact is that if you have a normally distributed random variable and you multiply that by any constant, non-zero constant, you're going to get another normal random variable. And so in other words, what I'm saying here is that CapX bar, by the central limit theorem, CapX bar is actually also a normal distribution, or can be approximated by a normal distribution. So now the question is, well, what are the parameters for CapX bar? I know it's normally distributed, so what do I use for those parameters? First parameter is the expected value of CapX bar, which I'm going to substitute in a cap S over N. Properties of expected value I can factor out. Again, I'm thinking of cap S over N as 1 over N times a cap S, and then I can factor out the cap S. I factor out the 1 over N, and I get the expected value cap S over N is the expected value cap S divided by N. Expected value cap S, we did that before, it's highlighted in red, so I have an N times the expected value cap X, and then the N's cancel off, and what you find is that the expected value of cap x bar is just the expected value of cap x. So cap x bar is often referred to as the distribution. It's a random variable, and it's often referred to as the distribution of sample means. It's a random variable distribution of the sample means, and the expected value of cap x bar will just be the same as the expected value of that common distribution cap x, the common distribution that all the cap x sub i's are distributed as, identically distributed as. All right, now let's look at what the variance of the distribution of sample means is. In other words, let's look at the variance of cap x bar. That's my second parameter in that normal distribution. When I list out the normal distribution as a parametrically, the second parameter is the variance of cap x bar. And so that's going to be the variance of cap s divided by n. This time when you factor out a 1 over n, it comes out as a 1 over n squared. So the variance of cap s over n is the variance of cap s divided by an n squared. The variance of cap s before we saw was n times the variance of cap x, so n times sigma squared sub x. So the n in the numerator cancels with one of the factors of n squared in the denominator, but you're left with an n in the denominator. So the variance of the distribution of sample means is the variance of the common distribution cap x divided by the number of terms that you're adding together. So as you add more and more terms together, the variance of the distribution of sample means is getting smaller. Okay, so that's those are the facts. So let me kind of piece together everything. So I got a cap x is cap x sub I is independent and identically distributed collection of random variables. Common distribution I'm going to use is cap x. Cap s is going to be the sum of those n random variables, and I'm assuming that I don't have a random number of terms I'm adding together. I have a fixed number of terms. It's not random. It's a fixed number of terms. Might be known, might be unknown. We'll do a couple of examples in just a second. And then the cap s is going to be have an expected value of n times times the expected value cap x, and the variance of cap s is going to be n times the variance of cap x. So that comes from the independent and identically distributed collection part. And then I have this other random variable, cap x bar, the distribution of sample means, and it can be listed out this way. The expected value of cap x bar is just the expected value of cap x, but the variance of cap x bar is the variance of cap x, the common distribution, divided by the number of terms that I'm adding together. And then finally, the central limit theorem tells me that if n is greater than 30, the random variables cap s and cap x bar can be approximated by normal distributions. Okay, so let's do a couple of examples. The first example, let's suppose that I have we have a company that sells 100 insurance policies for which benefit payments made to each policyholder are independent and identically distributed with a mean of 2475 and a standard deviation of 250. Now, I want to emphasize here that I don't know what type distribution. Parametrically, I don't know what type distribution this common distribution is. I just know its mean is 2475 and its standard deviation is 250. In fact, it might not even be a parametric distribution at all. It might just be given to me in tabular form as in tables. But the mean is 2475 and the standard deviation is 250. And then the last sentence here, let's approximate the probability that the total amount of benefit payments made to the 100 policyholders exceeds 250,000. So the total amount of benefit payments made to the policyholders would be the amount of benefit payment made to the first policyholder plus the amount of benefit payment made to the second policyholder, and so forth for all 100 policyholders. So I get a cap s equal to a sum of cap x sub 1 and a cap x sub 2 all the way up to a cap x sub 100. And the question is, well, what's the probability that this sum exceeds 250,000? So because I'm adding together 100 of these IID random variables, I know from the central limit theorem that I'm dealing with I can approximate cap s anyway with a normal distribution. And so I got a normal distribution here. Actually, the 2475 shouldn't be there. I don't know what happens on my spreadsheet, anyway, I wanted to hide that 2475 because that's not really that's not the answer. The first parameter here is the expected value of cap S, and the expected value of cap S is 100 times the 2475, 100 times the expected value of cap X, so it's 100 times that 2475. So actually the first parameter is 247,500 is what the mean of cap S is going to be. And now what about the variance of cap S? Well, that's the second parameter is the variance of cap S. And I know by being an IID collection, the variance of cap S is 100 times the variance of cap X, the common distribution. Now, I wasn't told the variance of cap X. I wasn't told the variance of the common distribution. I was told that the standard deviation was 250. So, of course, then the variance is going to be the square of 250. And so I'd get 100 times the square of 250 as the variance of cap S. And if I did the arithmetic right there, I think I'm getting a 6.25 million number. Okay, so now the problem is pretty easy. I've done the hard part. The question now is to calculate this probability that cap S is greater than 250,000, but I'm actually approximating that using the fact that cap S is approximately this normal distribution. So the first step in these probabilities with normal distribution calculations is to standardize the normal distribution. On the left-hand side of this last probability is I'm just going to plug in a cap Z, which is our notation for the standard normal distribution. On the right-hand side, if we go through the arithmetic on the right-hand side, 250,000 minus 247,500 is just 25,000. So I end up with 25,000 in the numerator. Square root of 6.25 million is actually 25,000 also. So my point is I just get a 1 on the right-hand side. Go through the arithmetic, you just get a 1. So my answer then is that the probability that the standard normal distribution is greater than 1, and I'll leave it to you to go through the tables and see that probability is a little over, close to a 16%, 15.87%. Or around 15.87% is that probability. Okay, let's do one more example. This is a very similar example. This is an SOA sample question. So I got a company sells insurance policies for which benefit payments made to each policyholder are independent and identically distributed, normally distributed with mean 2475 and standard deviation of 250. So now I've actually got that the common distribution is a normal distribution here. And the question now is to calculate the minimum number of policies that must be sold for there to be at least a 99% probability that the average benefit paid per policy will be no greater than 2,500. That's a lot. That's a mouthful. So let's try to kind of capture some information. First of all, I'm talking about a probability involving the average benefit paid per policy. So that's going to be my CapEx bar random variable. So I'm going to add up all of the benefit amounts to each of the individuals and then divide by the number of individuals to get the average benefit payment. And now let's try to make sense of what we're asked to calculate. It's the probability that the minimum number of policies that must be sold for there to be at least a 99% probability that the average benefit paid per policy will be no greater than 2,500. So this is we want to calculate N. N is the number of policies. We want to calculate N such that the probability, so I'm going to use 99% and instead of at least 99%. Let's just calculate what a probability equal to 99%. So probability of what? That the average benefit payment, that's the CapEx bar, will be no greater than, so that's that the CapEx bar will be less than or equal to 2,500. I want the probability of that event to be equal to 0.99. So let's start by calculating that probability. All right. CapEx bar, I'm going to assume is coming from a normal distribution let me rephrase that, because I don't have to assume that CapEx bar is coming from a normal distribution, because the common distribution in this example is a normal distribution. So in the expression that I have for CapEx bar equal to CapEx sub 1 plus CapEx sub 2 and so forth, all of those CapEx sub i's are normal distributions. When you add, and they're independent. So adding independent normal distributions is going to give me another normal distribution. And then when I take a normal distribution divide by n, I still get a normal distribution. So in this case, we're not even using the central limit theorem in this case, we're just we can conclude that cap x bar is a normal distribution just from the fact that the common distribution is a normal distribution, and adding or subtracting independent normal distributions will always give you another normal distribution. So again, I'm not using the central limit theorem actually in this problem. But again, cap x bar is a normal distribution, so the parameters, I need to figure out what the parameters are. So the parameter for the expected value of cap x bar, I know is the expected value of cap x just from previous a previous slide in the video. So I'm using a mu of 2475. And then the variance of cap x bar is the variance of cap x divided by n. So again, I'm not given the variance, I'm given the standard deviation of 250. So the variance is the square of 250. And so 250 squared ends up being 62,500. And so the variance of cap x bar is going to be 62,500 divided by n. Okay, so now go back to the last sentence. I've got I set that probability that cap x bar is less than or equal to 2,500 equal to 0.99, and the unknown in this equation is going to be an n value. And you'll see that in just a second. So I got 0.99, I just restated the probability in a different order here. And now the reason I did that is because the last expression, the probability that cap x bar is less than or equal to 2,500, cap x bar is normal now. So I go through the process. I just, first of all, standardize the random variable, the cap x bar random variable, by subtracting the mean, dividing by the standard deviation. So from 2,500, I subtract the mean, 2475, and I divide by the standard deviation, which is the square root of the 62,500 divided by n. So that becomes what's in parentheses there. On the left-hand side of what's in the big parentheses, the cap x bar minus mu over sigma, I'm just going to replace that with the letter cap z for the standard normal distribution. And then I'm going to simplify what's on the right-hand side. And if you'll simplify that complex fraction on the right-hand side, I'll leave it to you to show that what you get is just a 0.1 times the square root of n. So again, I'll leave it to you to simplify what's on the right-hand side, that complex fraction. And so what this says then is I'm looking at 0.99 being equal to the probability that the standard normal distribution is less than or equal to some z-score, the z-score being the 0.1 times the square root of n. Well, that implies that this 0.1 times the square root of n is just the 99th percentile of the standard normal distribution. And go to the tables and I find that 99th percentile of that standard normal distribution is a 2.326. So then I take the equation that's in red and I'm solving for n here. So I divide both sides by 0.1, then I square both sides, and I'll see that n is equal to a 541.0276 number. Now, n is the number of policies that are sold. It's not going to be a decimal number like that. And if I go back to the problem, the last sentence in the question says calculate the minimum number of policies. Well, this is telling me that I need at least 541 plus. And so the minimum number of policies, don't round off the n value, round it up. And so the minimum number of policies that I would need then for this probability to be at least 0.99 would be 542. If you have more than 542 policies, then the probability that that cap x bar is less than or equal to 2,500 would be even higher than the 0.99. Okay, so now this is actually the last learning video in the course. So at this point we're done with the learning videos. I hope that you found them helpful, and I wish you good luck in your studies for Exam P. Thank you, and now have a good day.